Welcome to today's class. Today we are going to study the behavior of the boundary at infinity of P. Recall that we are working with a Fuchsian group gamma and a hyperbolically convex, locally finite fundamental domain P for gamma. Let me start today's class with by recalling some notions from last time. So recall that we defined the notion of a gamma cycle in P bar as the intersection of any gamma orbit with P bar, where P bar is defined to be the topological closure of P in the hyperbolic plane H. We also defined the order of any given gamma cycle as the number of elements as the order of the stabilizer of any of its points. Since all the points in any given gamma cycle belong to the same orbit, their stabilizers are all conjugate to each other inside gamma. So they all have the same number of elements. And such number of elements is actually finite because P bar is contained in H. Right? So these groups consist of the identity and perhaps some elliptic elements. Right? But we saw that the discrete subgroups of PSL2R that consist only of elliptic elements beside the identity are finite, right? So that the discrete elliptic subgroups of PSL2R are all finite. So this is a well-defined positive integer. Recall also that we said that a gamma cycle is accidental if its order is 1. That is, if the stabilizer of any of its elements is trivial. And accordingly, a gamma vertex is said to be accidental if the gamma cycle it belongs to is accidental. Or, in other words, if that given gamma vertex has trivial stabilizer. So it's clear that if you give me a gamma vertex, that gamma vertex is either accidental or non-accidental. Right? So that's obvious. And on the other hand, last time we showed that if we are given a non-accidental gamma cycle, then, except possibly in a very specific situation, all the elements of that non-accidental gamma cycle are gamma vertices. Right? The only possible situation where this may not be the case is when the non-accidental gamma cycle has exactly one element, and that element is the fixed point of an elliptic element of gamma of order 2. Okay, and then we said that since we don't want to be always distinguishing this only possible situation where the non-accidental gamma cycle may have some elements that are not gamma vertices, we said that we are going to update our definition of what a gamma vertex is. So our new definition of gamma vertex is this one. So from now on, a gamma vertex of P is going to be either a gamma vertex with respect to the old definition, or following the old definition. That's what is written here. Or is going to be a set of the form P bar intersection with the set of fixed points of an element gamma of of our Fuchsian group, provided such intersection is not empty. So notice that that here it would have sufficed, given this that we proved last time, it would have sufficed here to say for gamma elliptic element of the Fuchsian group of order 2. But anyway, this is our new definition. Let's give an example to just kind of to visualize the difference between the old and the new definition. So suppose that this is so take the Poincare disk and suppose that the Fuchsian group we take is generated by the rotation of 180-degree angles around the origin. Then it is easy to see that the elements of the Poincare disk that have the positive real part form a fundamental domain for this Fuchsian group, and that the origin is now gamma vertex of that fundamental domain, and that according to the old definition, the origin would not be a gamma vertex. And that's the whole difference between our new notion and the old notion of gamma vertex, right? That we are adjoining just the elements of P bar that are fixed points of elliptic elements of order 2 of the Fuchsian group gamma. All right, so far for a quick review from some concepts of last lecture, and now we go on to studying the boundary at infinity of P. So recall the circle at infinity, which is defined if we're working in the Poincare disk model. This is just the unit circle in C or in C bar, whereas if we are working with the upper half plane, this circle at infinity is defined to be R bar, that is R union infinity. And its points are called the points at infinity of H, and of course none of those points belongs to the hyperbolic plane. Now, recall also that we defined P bar to be the topological closure of P in H, in the hyperbolic plane, so not in C bar. So the topological closure of P in C bar is going to be denoted P tilde. And of course, P bar is contained in P tilde, but we don't always have equality. And actually, the difference between P bar and P tilde is actually E. Right? This E, which is which is defined to be the set of points in the circle at infinity that can be approximated or approached by sequences of elements of P. Right? So it's the elements in the circle at infinity that are limits of points in P. Limits of sequences of points in P. Okay, so now this one, of course, it's a topological space on its own. It breaks into connected components. Among such connected components, we consider the ones that have positive Euclidean length and call them free gamma sites. To give an example, consider the Fuchsian group given generated by multiplication by 2. So it is clear that that this sort of circular stripe is a fundamental domain for gamma. it's a locally finite fundamental domain. And you see here, these two would be free gamma sites. Okay, so now here is an exercise which I would say is kind of hard. The exercise really consists on proving some statements from Beardon's book that I find I would say quite hard to prove. Namely that this set E may have uncountably many components, but that even if it has uncountably many components, only countably many of them are actually gamma sites, so only countably many of them have positive Euclidean length, and that every such every free gamma side, so every such component with positive Euclidean length, is necessarily homeomorphic to the closed interval. So this I leave you as an exercise. As I said, these are statements from Beardon's book. Another exercise, which I would say is also hard, is that a point in E may not be in the topological closure of a gamma side, and also not on a free gamma side. Right? So it is not necessarily true that every element of E belongs necessarily to a free gamma side, or is in the limit of in the topological closure of a gamma side. And the exercise is to give an example of a Fuchsian group gamma, a convex locally finite fundamental domain P, and an element of E, such that we don't have W on a gamma side, on the topological closure of a gamma side, nor on a free gamma side. Okay? Here also, when I say E may have uncountably many components, what I mean is to give an example of a Fuchsian group gamma and convex locally finite fundamental domain P, such that E has that property. Okay, and now I have this nice property, which is that if I take any element of P, so now there is this nice property which says that if I have an element of P and an element of E, right? So just like in this picture. So here this would be the element W of E, and this would be the element Z. Then this whole half shortest curve or half geodesic, which of course doesn't contain W, is entirely contained in P. So that not only can one approximate W with points in P, but actually one can approximate. These are points in P with which you can approximate the point W. And for the proof, just think of the use of the Beltrami-Klein model of the hyperbolic plane, and notice that well, P is convex, so P bar is convex, but not only that, P tilde is also convex. And being P tilde convex, we see that this has to be entirely contained in P, because P is open and convex. Okay, so this property is going to be very, very useful for the results today. Okay, so let's give one more definition for points at infinity. Right? So for points in the boundary at infinity of P. So a point there, a point in E, is going to be called a proper gamma vertex, of course at infinity, if it is the endpoint of two distinct gamma sides of P. Right? So the situation would be this. So if one can find two distinct gamma sides that go all the way to V, then we say that V is a proper vertex, a proper gamma vertex. And an improper gamma vertex is going to be, well, not the negation of being a proper gamma vertex, but rather being an endpoint, being the endpoint of, on one side, a free gamma side, and on the other side of a gamma side of P. In either case, we're going to say that V is an infinite vertex or an ideal vertex of P, or a vertex at infinity of P, or gamma vertex at infinity. Okay, so before going on to the main result of today's lecture, let us give an exercise. Let me give you an exercise that I'm going to use throughout the proof of this theorem. Namely, consider two vertical lines in U, in the upper half plane. So two vertical shortest curves, if you will, and fix and you see, and then consider points in those two vertical lines at the same height, right? So just like here, right? Or let's say slightly above them, but same height, right? So these are points, with the same imaginary part, of course. All right, and then keeping the height the same on both of these points, let them go to infinity. Let the imaginary part go to infinity. And the exercise is to show that the hyperbolic distance between the points at the same height, right? So same imaginary part, goes to zero. That this hyperbolic distance goes to zero. This exercise is actually not so hard if you go on and review some of the formulas that we established when we were studying the hyperbolic distance. And it has the following interesting consequence. So consider, let's say that I have here the Poincaré disk, a point in the circle at infinity, and two shortest curves that go to that point at infinity. Right? And on one of these shortest curves, take a sequence that converges in C bar to this point at infinity. Okay, and then what I claim is that it is possible to find at least one sequence on the other shortest curve that has two properties. One is that it also converges in C bar to the point at infinity, and second, the distance between the nth terms, so the nth term of this sequence and the nth term of this other sequence, that distance tends to zero as n goes to infinity. So why is this true? Well, just your original situation, that is these two shortest curves, map them to the upper half plane, sending this point to infinity, so that these two become vertical shortest curves, right? And then the image of this sequence becomes a sequence here that converges to infinity. Okay, and now take the points in the corresponding points in this other shortest curve, at the same height, you know, the nth term here at the same height as the nth term of the other sequence. And then of course this one also tends to infinity, and the distance between the nth terms goes to 0 because of this exercise. This I'm going to use throughout the proof of this theorem, which states the following. Take an element of E, right? So V is V can be approximated by a sequence of elements of P. And all right, so the statement is that for such a point, the stabilizer consists entirely, besides of the identity element, only of parabolic elements. So it's a parabolic subgroup. Right? So it doesn't contain hyperbolic elements. Right? In other words, if you give me an element here, it is never fixed by any hyperbolic element of gamma. That's the first statement. The second statement is that the corresponding gamma cycle, which technically I haven't defined gamma cycles for points at infinity, but what else could they be? Right? So that gamma cycle is finite. And moreover, V and all the elements in that gamma cycle are all proper gamma vertices. So they all look like here, like this picture. The proof of this theorem is rather long, and some parts are, I would say, quite technical. But let's start. So the first thing is that since V is a point at infinity, it cannot be fixed by any elliptic element of gamma. Right? And this is because we showed that every elliptic element of PSL2R has its fixed points outside the circle at infinity. Now, suppose that, contrary to what we want to prove, V is fixed by some hyperbolic element of gamma, nu, and take a nu to be the axis of that hyperbolic transformation. So recall that the axis of a hyperbolic transformation is the shortest curve that goes from one fixed point to the other, right? That joins the two fixed points of the hyperbolic transformation. Okay, so since Z, take any element of P, and so since V is in E, for this set in P, we have that this shortest, this half shortest curve is entirely contained in P, right? And so here is the picture. This Z is in P, and then together with Z, all this half geodesic is contained in P. And within that half geodesic, we can take any sequence of points that have geodesic that go to V, that tend to V as n tends to infinity, that tend to V in C bar. Okay. Now, consider the subgroup of gamma generated by nu. The axis is certainly stable under the action of that subgroup. So this subgroup, of course, acts here. Now, translate this subgroup and this axis to a standard example, right? So that the axis becomes a ray that goes from 0 to infinity, and nu becomes multiplication by a positive real number. If you think about that in those terms, in terms of the standard examples, you see that that there is some fundamental domain for that action contained in a compact subinterval of A. Right? For instance, let's say that the ray connecting 0 and infinity turns out to be just the positive real numbers, let's say, and that nu is multiplication by some positive real number lambda. Then the compact interval 1 lambda contains a fundamental domain or a fundamental set for the action, right? And then move it back to the axis, and you see that there is that the axis contains some compact subinterval inside which there is a representative for this action for any point in the axis. And so in particular, if now I take a sequence of points in this axis with the property of also approaching V, and with the property that the nth terms, that the distance between the nth terms of this sequence that I'm about to take and the sequence I already took here goes to 0. Such a sequence exists because of what I said previously. What happens, of course, is that for each member of the sequence, there is a representative inside here, right? And that representative is given by applying to it some power of nu. Okay. Now I claim that with this we can show that that there is some compact subset of H that contains all these elements for these same powers of nu, right? So which same powers? Well, the powers that bring the corresponding ANs inside this compact interval. So why does such a compact subset exist? Well, it's pretty much because of this property, right? Because if I consider the ball of, let's say, the open ball of radius 1 around AN, then for all large n, Zn belongs to that ball, right? Because the distance between the nth terms goes to 0. Okay, so this means that from some subindex onwards, I have this belonging to this ball, right? I mean, I just apply the same power. Okay, now for the previous ones, before you reach the index for which you know this, for the previous ones, of course, there is some distance between the m terms of the ANs and of the Zns. So the Zns certainly belong to some open ball of finite radius around AN. Right? So take any such for each of those. It's only finitely many. Right? And now close those balls. Right? So take the closed ball, which is a compact disk. All right, and then those apply the corresponding power, so that you move all of those balls to be centered at some certain points here in this. And then for the remaining ones, for the remaining points of the closed interval, take some closed ball of radius 1, say, again. Right, and then by compactness, we can extract a subcover, so that we can extract only finitely many of these balls, that still cover the whole interval, right? And somehow we still must have all of those points in the union of these finitely many compact disks. So this is true. Right, and maybe at some point one really has to change and take here 2 or 3, just to make sure, using the triangle inequality, just to make sure that all of them belong to this, all of these points belong to these finitely many compact disks. But okay, this is on the one hand. On the other hand, consider the set of powers of nu, right? I mean, these powers, right? The powers that move the corresponding ANs into the interval. So those that has to be an infinite set, right? An infinite subset of gamma. Why? Because if it were only finite, then the images of this interval would be only finitely many. So one would have then one would be able to cover the whole axis with finitely many compacts of intervals. But that's all of them have finite length, so that's impossible. This one has infinite hyperbolic length. So this means that this must be infinite. It cannot be finite. Right. Well, sorry. With if these were finite, when you apply to this interval, you would get only finitely many compact intervals that would contain then all of the ANs, but that's impossible because the ANs go to a point at infinity. Yeah, so that's the correct argument. So this has to be infinite. All right. So now we arrive at the following: the ZNs are in P. They lie inside P. Right. And each Zn is nu to the minus mn of this point of k. Right? So this means that there are infinitely many elements of gamma with the property that P intersects the corresponding image, P bar intersects the corresponding images of K. And this contradicts the local finiteness of P. So something must be wrong. So what's wrong? Well, we started with this assumption. So that's the assumption that must be wrong. And this shows the first statement of our theorem. So this shows that all the non-identity elements of the stabilizer of V are parabolic Morris transformations. All right, now the second statement, that the gamma cycle of V is finite. So this really follows from a theorem we already proved. So let me tell you which theorem. So remember this theorem, so that if we are working with a locally finite fundamental domain, and I take a parabolic element, so in our case it would be an element of the stabilizer of V, and I take a horocyclic region based at V, which is would then be the fixed point, and then only finitely many images of that horocyclic region meet D bar, so in our case P bar. Right, so let's go back. So the thing is now since the stabilizer of V consists entirely of parabolic elements besides the identity element. All the elements in this gamma cycle are fixed points of parabolic elements of gamma. And how can I determine them? Well, one way of determining them is by taking one horocyclic region around V and taking their images, right? Taking their images on their elements of gamma, right? Because these images are going to be horocyclic regions, then based at the corresponding point of the orbit of V, right? So, but only finitely many of those images can actually intersect P bar. So this cycle must be finite. Okay, and it remains to show that the last statement, right? So that the elements of the gamma cycle are all proper gamma vertices. So notice that it suffices to show that V is a proper gamma vertex. That is that V is the endpoint of two distinct gamma sites. Because then the behavior replicates all throughout the gamma cycle of V. So let's show that, and this is the most technical part of this proof. So what I'm going to do is I'm going to make some considerations about an arbitrary horocyclic region based at P, and then I'm going to see what happens when I shrink this horocycle. And kind of what I'm about to do is similar to what I did when given a point in given a point in H, I took first a compact neighborhood that then intersects only finitely many images of the fundamental domain by local finiteness, right? But this compact, some of these images may not contain the original point. So what I did was I shrunk the compact neighborhood by taking a sufficiently small compact disk, and for that I used that there were only finitely many images, right? So that for the new compact disk, if for any given image, if it intersected this compact disk, then it automatically contained also the point Z. So it's going to be similar to this trick. What I'm about to do. So take any horocyclic region based at V. Then we know that the number of images of this horocyclic region under elements of gamma that intersect P bar is finite. And here just to avoid confusion, I'm writing, instead of P bar, this closure in hyperbolic plane of P, right? So the topological closure of P in the hyperbolic plane. Kind of just not to confuse with P tilde, which is the topological closure of P in C bar, not in H. Okay. Just to avoid confusion, I use this notation. Okay, so this set of images of H under gamma that meet P bar is finite, although it may be that the number of elements of gamma that do the job is infinite, right? As we saw earlier, right? Like for instance, different elements of the different elements of the stabilizer of V, they are different, but they preserve H bijectively. So, okay, in any case, the set of actual images is finite, and being finite, I can extract from gamma finitely many elements that do the job. That do the job. Okay, now for any element of SH, of course, the image of H under gamma is a horocyclic region, and it is of course based at the point gamma V. Right? So that's obvious. Now, let's see what happens if that point is not in E. So if that point is not in E, then it's not a limit of points of P, right? So that means that there is an open Euclidean disk completely disjoint from P and actually from P bar. Right? So completely disjoint from P bar. All right, now notice the following. This is a horocyclic region. Its topological closure in H is closed in H, but it's not compact because it doesn't have this point at infinity. So this closure, which is actually this gamma of the closure of H, is not compact. But nevertheless, when I consider P bar intersect this topological closure, so the topological closure of this in H, it is contained in this compact set, right? I mean, you know, I delete from it this open Euclidean disk. So this intersection is contained in this, in this compact set, right? So now it's compact, right? So even though this one is not compact, I still know that this is compact. Okay. Now, so the situation is this one. So this is how the situation looks like. Now notice, I started with a horocycle H based at V, right? So H is somewhere here. Right? I mean, and actually, kind of the Euclidean size of H is not necessarily related to the Euclidean size of gamma of H, at least not a priori. Yeah, no, what I'm saying is that it is not necessarily true that this is just a copy of this. Okay, a translation. Anyway, if I start shrinking H, right? So if I start shrinking it, of course, gamma of H also starts shrinking. Okay? And if I shrink H sufficiently enough, this shrinks enough in such a way that it is entirely disjoint from P bar. Okay, and then I can shrink this for each point in the gamma cycle of V, right? And after finitely many steps, I finish, right? Because that gamma cycle is finite, right? And the final horocycle that I obtain, which is not the original H, right? It's kind of it's a smaller one, it's a Euclideanly smaller one. So that my set SH, of course, changes. It, of course, also shrinks, right? Becomes a subset of the original SH, but now has the property that for all its elements, gamma of V is in E, because somehow I already excluded all the possibilities when I already excluded not all the possibilities. I excluded all the points for which it didn't happen. So, okay, and this implies that the images under the elements of SH are contained in the gamma cycle. The images of B, right, under the element of SH are contained in this gamma cycle. And the other inclusion I leave as an exercise. All right. Now, of course, I can assume without loss of generality that I'm working in the upper half plane, and of course, without loss of generality, up to perhaps conjugating gamma inside PSL2R if necessary. I can also assume that my point V in E that I took is actually infinity. Then the stabilizer, which I know is a parabolic subgroup, it consists entirely of horizontal translations, and I know it's cyclic, so it's generated by some horizontal translation, and up to taking the inverse of that generator, I can assume that I take a generator given us by a translation to the right, by some positive real number, beta. And my Hor cycle then takes this form, right, of all those elements of U that have an imaginary part greater that some fixed positive real number. Okay, now think about P, the original P, the original convex locally finite fundamental domain. What I'm going to do is I'm going to see from where to where it runs horizontally. So I consider the infimum of the real parts of its elements and the supremum of the real parts of its elements, right? To see from where to where it runs horizontally. So it runs from A to B. Of course, A is less or equal than B. That's obvious. And I leave you as an exercise to show that these are actually real numbers. That they are not, that A is not minus infinity and that B is not plus infinity. Okay, now I claim that the stripe, the kind of the vertical stripe that inside the upper half plane goes from A to B doesn't have width greater than beta. That is, it has width at most beta. Right? So, in other words, of course, A is less or equal than B, but what I'm saying is that B is less or equal than A plus beta. Where beta is taken from the generator of the stabilizer of V. Okay, suppose that actually B is greater than this number. Right? So I am in the situation you are seeing in this figure. Okay, now because of the way A and B were defined as supremum, as infimum and supremum of the real parts of elements of P, I can take a point sufficiently close to this vertical line determined by A and to this vertical line determined by B. And by sufficiently close, what I mean is that, for instance, this point is to the right of the vertical line at A plus beta, which I assumed to be less than B. And similarly, sufficiently close here, what I mean is that the distance between this, the distance between the real part of this and A is less than B minus A plus beta. Right? So I consider this vertical line, where here this width is equal to this width, and I just take a point to the left of this vertical line. Okay, so I took these 2 points. together with these 2 points, this shortest curve is entirely contained in P because P is convex. But also, since V is in E, this vertical shortest curve and this vertical shortest curve are entirely contained in P. This is what we argued here. Right? And that we already used before. Okay, so this shortest curve is contained, this shortest curve is contained, this shortest curve is contained. Okay, so this entire hyperbolic triangle is contained in P by convexity. All right, but then you see, then you can take some point. You can take some point here. So let's say a bit further. So around here, and that point is equivalent on their translation by beta to a point here. Okay? But translation by beta is an element of gamma v, so it's an element of gamma. So you obtain 2 points in P that are gamma equivalent, but that goes against to the very definition of being a fundamental domain. So this must not happen. Sorry. So this must not happen. So this must be the case. Okay. Now let me back off a little bit and see what I have just shown. So I just showed that if I'm given my convex locally finite fundamental domain that has a v in its boundary that has in this v in its boundary at infinity, then that fundamental domain must be contained in a stripe of width at most beta. That's what I just showed. Okay. In other words, what I just did is valid not only for P, but actually for any locally finite fundamental domain that has this one, that has this point in its boundary at infinity. Okay. Now, notice the following. If you give me any element of gamma, I have this intersection different from, I have that this intersection is not empty if and only if this intersection is not empty. And this is obvious because going from here to here, you just apply H inverse, whereas going from here to here, you just apply H. Right? But this is precisely the condition of this image of H belonging to IH. Right? I mean, just look at the definition of IH. Okay, but this is equivalent to this, that for some SH, for some gamma in SH, the images are the same. Yes, but you see, the images being the same, since these are both holocyclic regions, that is equivalent. That implies that they are based at the same point, right? So this means that this is equivalent to saying that H inverse of V is equal to gamma of V. So for this gamma, V is a fixed point of H of gamma, of H preceded by gamma. Okay? But okay, but so what we have shown is that for H in gamma, this being not empty, if this is not empty, so if it satisfies this, so if this same holocycle, if this same holocyclic region intersects now this topological closure of P, the topological closure of the image of P on their this element of gamma. If it intersects it, then then this very same V lies on in the boundary at infinity of this other fundamental domain for gamma, which is also a convex locally finite fundamental domain for gamma. Right? Why? Well, because of this, right? Because this is non-empty if and only if this happens. But you see, this tells you that V is in the Euclidean boundary of H of P. Okay. Now, then this means that if this happens, then this fundamental domain must be contained in some stripe of length at most, of width at most beta. Now this stripe cannot overlap this stripe here, right? Because if it overlapped it, then I could find some point that is at the same time in P and in H of P. Right? So it cannot. So what by this what I mean is that it can overlap only in the overlap may happen at most on one of these two shortest curves. Okay, but yeah, and you see, whenever there's an overlap, then the whole thing belongs, right? I mean, so this means that I have exactly one gamma side kind of on this side of P, and that for exactly one element of gamma, right? That goes all the way to V, which is infinity, and exactly one here. Right? So I conclude that from some point here, from some point on this vertical shortest curve, and from some point on, what I have is gamma sides of P, and they go all the way to V. So V is a proper gamma vertex. So I am in this situation, and this finishes the proof of this theorem, which I would say the proof is I would say maybe quite technical, I would say. Okay.